Alright, welcome back. Today we're going to be doing firing of action potentials and neurotransmitter release. I apologize for the late upload. I've been studying for my final, which is tomorrow in a few hours, and been really studying on that, so I apologize for the late upload again. So I made this video as simple as possible. I made it overly basic, but it's still a good amount of information, so don't get me wrong on that. I just made it super basic, and I'll post the advanced version of this in a few days. So I just want to get the basics down so you watch this video first, and it makes more sense. We can just jump onto the advanced version right after this. Okay, so we're into about action potentials. So I told you action potentials are basically like the electric signal the neurons use to communicate with around our body. So neurons would communicate between another neuron. It could communicate, to a muscle, for example, even the heart to muscle. So what's happening here? So how is the action potential actually developed? So the first step is the neuron acquires some kind of signal from the dendrites. We spoke yesterday about the dendrites and how they receive signals. So the incoming signal can be from another neuron, right? Or it can be, coming from the brain, for example, right? The brain sends response, and the response is given into the neurons from the dendrites, and so that's basically like the incoming signal. Now, this incoming signal, it opens sodium channels in the cell body. So sodium rushes into the cell. See how sodium is positively charged? So since sodium is positively charged, we're going to raise the voltage of the neuron. So the membrane potential or the voltage rises of the neuron. The very important thing you know is voltage. So the voltage of the neuron must hit the threshold to fire the action potential. So right here, what I said, this has nothing to do with we haven't reached the action potential yet. We're just basically prepping the action potential. We first get the signal to the neuron, which comes from, like I said, from another neuron usually, or, from a channel, for example, or something like that. Somehow sodium gets in, whether it's from the dendrites or some kind of chemical response. So really what you need to know is the sodium goes in and the voltage goes up. This is a very famous graph. I simplified it completely. I left out about most of the information, but I put the most important thing for this particular video I'm doing right here. I'll make the more complete one tomorrow, the next day. But this is known as the action potential graph. Do you see at negative 65 millivolts? We classified that, or we in books or whatever, it's known as the resting membrane potential. This is when the cell is at rest at negative 65. And you see the green dotted line, it goes, across. That's negative 65. Negative 40 millivolts is known as the threshold. The threshold is different, within every neuron. Just for the sake of example, I put negative 40 millivolts as a threshold. So what's going to happen is, ow, that's my leg. Hit my desk. So when sodium enters the cell, right, the voltage goes up. So from negative 65 to negative 40, the voltage is going up, right? That's voltage, right? We're getting less negative. So basically what's happening is sodium enters. Sodium enters the cell. Now it's basically more sodium is entering, and then we get to the threshold. Then the cell gets super excited. It basically develops electricity and shoots it. It shoots it through the axon. If this picture looks familiar, it's because I plagiarized it from my last lecture, my last video, so yeah. So it basically fires it down the axon. It goes like that, down the axon, right? We got sodium, so we in the last slide, right? We got sodium channels, whatever. Sodium entered, a lot of sodium entered, so we reached the threshold, right? And the action potential, AP, develops right here, And once we reach -40, it goes down, down the axon, super fast. Okay? And it doesn't go infinitely high. It levels off, right? The voltage doesn't go up to 1,000,000, right? It just usually levels up at 30 millivolts and then we'll go back down. There's something called the refractory period and absolute refractory period. I'll do that in the next video, but don't worry about that for now. All right. So now we reach the axon terminal. So the electrical signal reached the axon terminal. So there's a reason there's a magnifying glass here. So there are these little knobs looking things at the end, right? The axon terminal. If you zoom in, there's basically these vesicles or little mini storage bubbles, I like to say. And these little storage bubbles contain something called neurotransmitters or hormones. Okay? This is what communicates cell to cell. So what essentially is going to happen is that these neurotransmitters are going to be sprinkled onto the muscle or onto the next neuron in the cycle in this little pathway. And that's how we transmit information from neuron to neuron or neuron to muscle. This neurotransmitters is what connects this connects the signal. It's not the electricity. The electricity is only confined to this one neuron, but to get from the next cell over, the next neuron over, or to the muscle cell that we're trying to communicate to, we had to use neurotransmitters. Okay, so what happens? It's like we said, the action potential regenerated goes down the axon, right? This is the axon. We talked about this. It goes down the axon. We reach the end. Okay, we reach the end. So this area right here was originally a resting membrane, right? Membrane potential. It was fine. Nothing was happening, right? The vesicles were nice in their little homes, not doing anything. Now, the action potential arrived, the voltage goes up, right? As we said, right, is the action potential is, it's highly charged, right? It's around 30 millivolts. The voltage is up, right? So this area of the neuron, the voltage is high. There are these very special voltage-gated calcium channels, not sodium, calcium channels in the axon terminal. There are many of these. When the voltage goes up, the door opens and calcium from the outside can rush into the cell, into the neuron, into the axon terminal, more specifically. So calcium just like literally floating around the neuron. And then when the voltage goes up in the axon terminal, these little doors, like pretend there's like a door here, or there's a door here, and it opens up when the voltage gets high and the calcium rushes in. Now what's going to happen is these vesicles were not doing anything. They were just sitting in the axon terminal, not doing anything. They were all prepped to go, right? The vesicles have neurotransmitters in them. The neurotransmitters can be anything. It could be dopamine. It could be serotonin. It could be acetylcholine, for example. It could be epinephrine. It can be norepinephrine. It can be whatever this neuron was born to do. So during development, or actually, there's I'll talk about something right after this. Hopefully I won't forget. But let me just get back to this, and I'll explain. So these calcium ions we let in are basically attracted to the vesicles. They don't necessarily bind, but they get close to it. And when they get close to it, it basically causes the vesicle to go towards the outside, right, to the axon terminal, to the very edge. And the vesicle basically rips open, it dumps its little neurotransmitters that was holding into the synapse. The synapse is the gap between a neuron and a muscle or a neuron to another neuron. That's what the synapse is called. So these neurotransmitters that we released are going to basically bind to these receptors. So there are receptors on the place we're going to. So it could be a muscle, it could be a neuron. Doesn't matter. There are receptors on the receiving end that will bind, these receptors will bind, the neurotransmitters will bind to the receptor. And this will cause, contraction to happen or signal to get passed on. Passed on. Okay? So what would usually happen now is the neurotransmitters bind whatever, and sodium rushes in. Oops, that is too thick. It's a bakery. Sodium rushes in, right? We have sodium channels, sodium rushes in. Notice how this is exactly like the beginning, right? Sodium rushes in. Pretend this end stage was a neuron. Oops. Pretend this was a neuron, not a muscle. It was a neuron. So this would be the dendrites, right? Basically, what happened is like a receptor bound to here. There's a receptor, there's a neurotransmitter. A neurotransmitter binded. It caused sodium to open, sodium to rush in. We got another action potential. This is how neurons communicate with each other. Okay, before I forget, I almost forgot. So this is a little fun fact. My professor here at UCSD is doing research on this actually, and it was originally thought that neurons. So pretend we have a neuron, and it was born to be a dopamine neuron. Okay, so that what it means is dopamine. It's dopamine. Dopamine. Cannot speak. Okay, the neuron was born to be a dopamine neuron. What that means is that the neurotransmitters in that neuron is dopamine. We originally thought that it was impossible for the neuron to change which neurotransmitter it's going to release. That was proved wrong by one of my professors. I actually had a class with him. He proved it wrong, and he did studies on this. He was he works on mice, and he measured the neurotransmitters in mice, and they had something called GABA, GABA neurotransmitter. If you did not know, GABA is an inhibitory neurotransmitter. You don't worry about it what it is. I'll go over it later. But the mice were exposed to exercise, right? So they got on a wheel or whatever, and they did their exercise. Then they realized that after a long time of exercising, the 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 neurons change which neurotransmitter they release. They saw now it releases glutamate, which is amazing. Okay, so this is one reason why maybe if you feel depressed, for example, right, and then you go to the gym and then you feel great, could it be neurotransmitter switch? Right, so neurotransmitter switches, the neurotransmitters is switching in the neuron. So it went from GABA to glutamate. So that's called neurotransmitter switch. So is this the reason why we feel good when working out? Right? I mean, it could be there's other psychological effects, energy, ATP, whatever. But is this the underlying reason behind this? And my professor is still doing research, on it. It's amazing. So his name is Dr. Nicholas Spitzer, very famous, and he's best friends with the guy who won the Nobel Peace Prize at Scripps this last year on click chemistry. I think it was Dr. Gary Sharp, or I don't know his first name, but I know his last name is Sharp. So they're best friends, and they go to lunch together all the time. So yeah, thank you for listening. Please like and subscribe if you found this, helpful at least. Thank you again for 29 subscribers now. So we're slowly getting up there. So all right, later.